Hi, in this video, we want to take a look at other methods of modeling spatial data when we have aerial data. All right, so when we say aerial, this means that I have something like neighborhoods, counties, states, countries, so geographic regions that we represent with polygons. And then for each region, we have data values. So how this is different than other spatial data is that other spatial data that we could be talking about will be like points on the ground. And I want to model like, individual locations, spots individually. Here we have regions. So maybe I have data about like, from each county. And, I'm getting that from like the government, the county governments. And so there, it doesn't make sense to model points on the ground. So now what I want to do after I get data pertaining to each polygon, I want to do some kind of modeling to get a better idea of what's going on. All right, so what we're going to do is we're going to look at some other methods. We've looked at some previous ones, specifically with autoregressive techniques and simultaneous autoregressive and conditional autoregressive. And we're going to just take a peek in this video at some other techniques that we've got. So the examples, what we're going to go through are from Applied Spatial Data Analysis with R, Chapter 9. Here are the authors of the textbook. Here's the textbook's website, and the textbook is free to download if you are a UCF student. All right, so let's get into it. All right, so the first thing I want to talk about is not other methods, but the idea of just using a regular linear regression model. So in that situation, what we would be doing is if I had covariates for each of the areas, each of the regions, what I could do is completely ignore the spatial aspect of things and just run a linear model. And that could actually be a pretty good model to go with. Well, if I can do that with a linear model, I can do that also with generalized linear models or generalized additive models. All right, so let's go ahead and take a look at generalized additive models. So these are similar to generalized linear models, but they also allow for including nonlinear terms in the linear predictor terms. All right, so the formula itself can contain linear, polynomial, and spline terms if we so desire. And different types of nonlinear functions may be chosen using the S function in the MGCV package. All right, so let's go ahead and build a model. What we're going to do, we're going to take the covariates that we feel that are important for the leukemia examples that I've been talking about in several videos, and we're going to add an isotropic thin plate regression spline to the model. And so this is effectively semi-parametric trend surface, and this is how we're going to add a smooth spatial structure to the residuals we fit. All right, so what we're going to do is that we're going to take the coordinates for the locations at each of the regions. So here we've got X and Y. And then we're going to put those into the S function right there. So here, this is the standard formula that we've been looking at over and over and over. And then we just add the spatial coordinates in the S function to take care of it. And just like before, we're using population to determine weights, so the populations of each of the regions. And here is our data frame. Now, without this S, this is a regular GAM without considering spatial data. The S is how I'm choosing to pull that in. All right, so now once I get my model, let's go ahead and compare it to a linear model without the S. So here I've got a linear model where I'm using the same weights, same formula, except for we don't have the S of X and Y. And here is my generalized additive model. And we're going to use the chi-square distribution to run our hypothesis test. And we can see that it looks like we do not gain sufficient informative value from by adding on the coordinates. That's interesting. That surprised me. That really surprised me when I first saw that. So we conclude that the linear model and the generalized additive model are equally informative for this data set. Well, the linear model, so without the spatial coordinates, is simpler. So it's simpler in mathematical structure because the generalized additive model is more complicated, and it has fewer terms. Therefore, we would want to use the linear model. All right, well, something that is important to realize about generalized additive models is that our degrees of freedom are not necessarily integer values. And so if I want to start looking at, start doing computations that involve degrees of freedom, I'm going to need to get that out. Here, this function, the EDF, that is an estimated degrees of freedom. And so the degrees of freedom can be kind of complicated, and there can be different ways to compute them for the more complicated models. So we're just going to use the estimated function and just grab it and go. Now, another option that we would have would be for us to go through and model the cases with a Poisson regression. All right, so what we're doing here, so previously we've been talking about cases, log cases rescaled by population was our Z. Now, instead of going with that modified target variable, we're going to actually just go with the raw cases per area with Poisson regression. Now, this offset is treated as a constant term, and this is treated as a non-statistical object. It's treated as a constant. We are not going to get a standard error on this item because of the offset function. And so here's my data for any standard generalized linear model. Here are my weights. Now, before doing this video, I went ahead and ran this code without the start, and I got the coefficients. And then just to make things run a little bit faster, when I was running the code afterwards and checking what's going on and preparing for this video, I went ahead and just put in the coefficients up to rounding into the start value. And so that way it'll converge as fast as possible. Now, if you look at the cases are not actually integer values because the raw data did not perfectly correspond to the regions in the data set. And the authors of the data set went through and estimated what the counts actually were for the cases in each region using the data and using population size. And so because cases are not integer values, there's a bunch of warning messages that pop out. And I went ahead and suppressed them just because it just distracts from what we want to look at. All right, so now let's go ahead and check out our Poisson regression model. So here we have our formula. We see the family and the data and all of that. And we can see that all of our predictor variables are statistically significant. And here the dispersion parameter for the family is taken to be 1. So let's go ahead and plot what we've got going on here. And so here I'm plotting the residuals. So we can see where is our model farther off from what we actually observe. And we can dig in and try to figure out what's going on, or this can help us reach a decision on should we keep a model or reject it. Now we can also do a Poisson regression model with a generalized additive model. And so all I need to do is with the GAM function, I change family to Poisson, boom, we got it. And here we can see that all of our predictors are statistically significant. Our adjusted R squared is 0.43, not very good, not very large, but it looks like there is some aspects that are being explained with the model. Now let's go ahead and use Anova to compare the two models. Let's see if these two models are equal to each other from a statistics point of view. And so here we have a small p-value, so I conclude that they are statistically different. Therefore, I want to go with the one that does a better job performing. And so we have 0.43 for R squared adjusted, and we have it doesn't actually say. All right, so we would go with the GAM on this one. It's more complicated and it's got the spatial aspect included. So between the two, I want to use the generalized additive model instead. And here we can go through and estimate the degrees of freedom for the generalized additive model. We can see that's 29. That's a pretty big jump compared to the other one. Now, something that can happen is that we could have over dispersion. And so it looks like things are too spread out for things to technically be the Poisson distribution. So one way to address that is to go with the Quasi-Bassan Distribution. So here you'll notice that I'm doing the generalized additive model. Here I'm doing the generalized linear model. And now let's go ahead and take a look and just see how these compare to each other. And so we have the generalized additive model with Quasi-Bassan, generalized linear model, Quasi-Bassan, generalized additive model, and then generalized linear model. And we can see that, you know, we have some differences between them. Now, how to interpret this is that what this is doing is that this is evaluating, is there a statistical difference between the first and second? Is there a statistical difference between the second and third? Is there a statistical difference between the third and fourth? And so how to interpret this, it gets kind of nuanced on us. Here, what I would do, I would probably use the generalized additive model with Quasi-Bassan regression. For this problem here. All right, so now what we would like to do in this next part is I want to build a bunch of models, and I want to actually just pick a few that I would actually consider using. And so what I'm going to do, I'm going to build a linear model, I'm going to build a conditional autoregressive model, simultaneous moving average model, simultaneous autoregressive model, and I'll start using mixed spatial functions, and I'll even pull in a few others. And I want to build the models, and I want to decide, hey, what is the best model to actually work with? So how I'm going to approach this is that I'm going to create a list, and in each slot in the list, I'm going to have a model. And that way I have all my models in one spot when I do my coding, and I can do my computations to get the comparative statistics easily. First one I'm going to do is a linear model, the simplest one possible. I'm not considering anything about the spatial aspect at all with this one. Now what I'm going to do, I'm going to use the spatial reg package to get a conditional autoregressive model, a simultaneous moving average model, and a simultaneous autoregressive model for each of these. And you'll notice that I'm saving it inside the model, or the list of models. Then I'm going to do the same thing with lag, simultaneous autoregressive linear model. We're going to go Durbin, lag, and mixed as the types. Durbin and mixed are actually the same, by the way. But if you put either name in to the package, the function, we'll go ahead and actually get the same model regardless of how you call it, the two different ways. Now here we're going to get, for the errors, the simultaneous autoregressive linear model. Once again, Durbin, error, and E mixed. Durbin and E mixed are going to give us the same model, but I put them in here so that you can see the variety. Now here, I'm using the mixed spatial package for simultaneous autoregressive maximum likelihood. Here I'm using quantile regression. And you'll notice that I'm using the same weights in the same formula every single time. Now, I'm going to go ahead and use the spatial, I can't even pronounce it right, but this is a spatial package for when the distribution is not like symmetric, and we're doing a spatial reg off of this package. And here are the types of model that we're going to be running. We can see that we have lag, error, autoregressive, and we have ordinary least squares. And then I'm going to run that generalized additive model we talked about previously. So at this point in the code, what we've got is a list of models, and each entry is a different model. Now I want some way to compare the models. So I chose AIC. Why AIC? Well, because it does a good job of considering how well the model fits with the data and the number of parameters, aka how complex the model is. And so I'm trying to consider model complexity and model fit simultaneously when I use AIC. Also, AIC is well established, well understood. It's definitely reliable. So what I'm going to do, I'm going to use a for loop for each model in the list. I'm going to compute the AIC. Now it's going to work out that not all of them will work, though. This is the AIC function in base R. And you'll notice that I'm running a try around the code. What this is saying is, if there's an error, don't shut down, keep going. The silent says, if there's an error, don't let me know about it, just keep on going. And after this ran, when I was preparing for everything, I took a look at the output. So I knew where the errors happened. So now what I want to do, I want to take a look at the AIC, and I want to see how do they compare. And all of this next part is just all about getting a visualization. All right, so off of this modeling, we can see that the linear model is actually the best AIC. So when I consider model complexity and informative value together in the AIC calculation, linear model came out on top. So that means that the spatial aspect really isn't coming to bear that much in this data set. Now, if I'm in a situation where I have to include some kind of spatial components, then the conditional autoregressive model looks like it would be a pretty good choice. And we can definitely, we can see how these came out. And we can see that After linear model, we have all of these coming in. It looks like the error simultaneous autoregressive models didn't perform too well. And then the lag simultaneous autoregressive linear models performed the worst. So I definitely would, lean away from those. Now, something also to note is that the AIC is all pretty tight on all of these. And so really any of these wouldn't be like a bad choice, but by the scoring, linear model came out ahead by a little bit. That also means that if the data was to change just a little bit, we could see a different order aspect. All right, so the models I would choose would either be the linear model, which doesn't consider the spatial component at all, or I would use the conditional autoregressive if I have to use a spatial component for sure. Let's say my supervisor or the client absolutely wanted a spatial component in there, even if it really didn't contribute to the performance of the model. Well, that's all I've got for you. Take care and goodbye.